So we're here today with our first of the enrichment lectures for the cybersecurity course. And I wanted to begin with a little bit of contextualization around what we're kind of doing on the first assignment. So over the course of the first week of class, we've introduced a series of technologies, and now we're going to apply them to security concepts, beginning with a number of cryptography techniques, and sort of the most fundamental of all cryptography techniques is the cipher. So I'm going to introduce ciphers here today, and I'm going to do so by creating a document about ciphers, sort of live in front of all of us, so we can see that process. And I'm going to do it based on a textbook. I call it the crypto book, and I think that's what it calls itself. It's the companion text to a graduate course in applied cryptography at Stanford. So some of the terminology we use is going to be borrowed from that course, and I have a link to that course provided as a optional text in the syllabus, but we're going to be going over that today. We want to introduce ciphers because they will see use on the first assignment and because they're independently interesting to study. So in order to do this, I'm going to be working in uh, a sort of interesting combination of technologies here, and I'm going to introduce them one at a time. So first, I have Visual Studio Code pulled up. Excuse me. And this Visual Studio Code has a remote server that is hooked up to a Linux backend. So there is Linux running underneath this Visual Studio Code. And on top of that Linux, we are running the Quarto library, which is developed by Posit, the creators of RStudio, and formerly RStudio Cloud, now Posit Cloud. So I've sort of arrived at this combination of technologies in conversation with my colleagues and with the students in this course. And we're sort of going to use the Markdown way of writing up some of these descriptions. And you'll see that this is familiar to how I've developed a bunch of the course materials, but I want you to see the process. So whenever I start working with one of these documents, I have to begin by creating sort of a title. And today that title is going to be Cipher. So I make a little title section. I specify that I'm going to give it the title, and there are a variety of built-in things we can specify in Quarto Markdown, and then that will close out my title. I'm going to use Control-Shift-K to render that, and this is all essentially running at a web server. There's nothing too exciting going on here. With that title added, I can now go in and I can sort of start typing some text that'll be reflected. So we'll say Cipher. I'll Control-Shift-K, and hopefully this will work. And then I have Cipher showing up on the other side of my screen. The initial title up here, this is going to refer to things like what this web page would say its name is if I opened it in a web browser. Today I'm going to be working in a certain format, and that's my preferred format for doing these things, which is HTML. I'm going to use the Darkly theme. I am really invested in using monospace fonts. And then I'm also going to write some code, and I want that to have the same highlight style I'm used to, which is GitHub. So when I do that, nothing much will change at first, but you notice that the font has changed to now be specifically a monospace font. So all of the letters are the same height, width, depth, and so on. To begin with, let's just do a bit of a Quarto Markdown demo. The first thing I want to show is that essentially we're working in Markdown, right? You've already seen sort of the octothorpe / hashtag / pound signs come through to make section headings. I tend to have a preference to write things inside of bulleted lists, so I have a tendency, I should probably turn off Copilot, to write things inside of bulleted lists. And then separately, I have a tendency to write code blocks. My Quarto Markdown is backed up to an IPython kernel, and sort of the work I'm going to be doing today is going to be running through that IPython kernel. Now, the IPython kernel is a little bit different from Python itself, but similar enough we can use it here. So many of the things that I will use inside of Quarto Markdown are things that you could use inside Jupyter Notebook. Many of them work inside something like Google Colab. And in fact, this whole thing could be done on Google Colab if I could render it as prettily as I would like. The most basic thing to do inside Python is to print hello world. And we close that with triple quotes, and then I can render this as well. I have a tendency to write code blocks interspersed with bulleted lists. Now, one of the reasons I arrived at using the Python kernel for this is the Python kernel has these things in it called line magics, and line magics enable us to do some of the things that we would often want to do at a command line, but I'm sort of able to preserve what they're doing. So let's do one example. I'm going to use one of my favorite and most basic Linux commands. We can try a Linux command via a line magic. Line magics are prefaced with a single %sign. So I'm going to open a code block with triple backtick. I'm going to specify that I want to use the Python kernel. I have to specify the language I'm using. I'm going to use an internal line magic sign within the Python kernel, which is going to specify that even though I am running with the Python kernel, I'm not going to run specifically a Python command. I'm going to specify a Linux command, and then I'm going to close this, and then I'm going to run the code. This is going to reveal a little bit about what's going on in the back end here. So one of the things I'm looking at is that we have Cipher.qmd, which you see on the left side of my screen. That is the Quarto Markdown document that I'm working with. Then we have Cipher.html, that is the rendered visible document that is on the right-hand side of the screen. I suspect that Cipher.quarto.imb is one of the things used by the Python compiler. I don't actually know how the Python kernel works. Seems cool. Not sure what's in Cipher files. Usually when I go in there, I find things like images, which is quite nice. And then you can see that I was goofing around a little bit with the C programming language in here. And so I'm going to go ahead and actually get rid of those real quick because I think they're distracting from my demo. So let me take care of those. And see if this looks a little smoother. So there we have it. I pulled up a terminal off screen, typed in some quick commands, and changed the underlying file system. I want to emphasize we can do terminal commands in QMD, but it isn't always the easiest way to do them. The benefit of using this technique is scientific and technical communication. It is not speed, it is not precision, it is not accuracy. So the reason we have pulled this up is actually not that this is a technology demo of a way to do things in Quarto Markdown, but in fact that this is a way to learn about ciphers. So let's begin with an introduction to ciphers. So I am using material adapted from CryptoBook. Let's see if I remember how to do Markdown hyperlinks. Is it perhaps like this? And you can go ahead and check this out. It's very nice. It's a lovely book. The thing that they introduce first in this book is something called the Shannon cipher. So the first, well, I guess there's a chapter 0 or chapter 1. I don't actually know what it is, but the first of the chapters in this book is chapter 2. I think from time to time we make fun of languages for being 0 or 1 indexed. Python is 0 indexed. R is 1 indexed. There are algorithms that prefer both, most commonly heaps, which, let's see, we want to say when embedded in arrays are often 0 indexed, or 1 indexed, to avoid an off by 1 error. CryptoBook is 2 indexed. I was surprised as well. Um, so they are going to introduce this thing called the Shannon cipher. In the crypto book, this is 2.1, and they call it Shannon ciphers and perfect security. I am going to match that naming scheme. Shannon ciphers and oh, I cannot spell. One of the problems with writing code live is how embarrassing it is. Let me take a sip of coffee. And I should be rendering this as I'm going. So, Shannon ciphers and perfect security. In the crypto book, the first thing they do is they introduce this. Introduce a Shannon cipher with a mathematical definition. Mathematical definition. And that is this thing. And that is not what it looks like in the crypto book. And part of the reason for that is that we've got a squiggly E here. So I'd probably have to do something like, ooh, do I have insert turned on? That's weird. Equals, probably italicized. I don't actually know why this is doing insert sometimes and not others. That just caused the E to go away. I need a script E, and I don't really know how to get one. So what I'm going to do instead is I'm going to use Python. And what I'm going to do is I'm going to define a Python cell that is going to describe what a Shannon cipher is. So a Shannon cipher accepts two things. It accepts a pair of functions, and these functions are called E and D. And then we can just think of this as returning ED. It sort of just puts them together as a pair. Right, so how are we going to use this? Well, separately, I should say what I mean here. A Shannon cipher is a pair of functions. And this is bolded. Shannon cipher is a pair of functions. What is the nature of this pair of functions? Well, the first one is the function we denote E, which is the encryption function. The first function, denoted E, is the encryption function. It takes two inputs. The first is some key, K, and the second is some message, M. I often denote the message as MSG, because MSG and KEY have the same number of letters. What is the output? It produces as output a single output. So in Python, and in fact in the immediately prior line of Python before this, I used a multiple return. I said a Shannon cipher accepts an encryption and decryption function and returns them. It is functionally identical to a tuple, but it predates the understanding of tuples, so we format it as a function. We're under no obligation to do this, right? It is perhaps more reasonable to say functions must have some fixed return value. This has commonly been the case in mathematics. And so in the case of a Shannon cipher and the encryption function of a Shannon cipher, we say we have a single return value. Ooh, I should put colons here. And this is not bulleted. I'm getting sloppy. A ciphertext is produced as output. And we usually denote that C. So, what does this look like in practice? We assume the existence of some encryption function. I'm just going to say for now, E is going to equal lambda none, I guess, which I think is the sort of absolute minimal encryption example. And then we say C equals E of K and M. And what are each of these things? Well, K is the key, and for now we'll just denote that as key. And M is the message. So we have some key, some message. We can create a function that is the encryption function of K and M. Let's see. Ooh, lambda takes 0 positional arguments, but 2 are given. This is a good point. I specified that the encryption function E is an encryption function that accepts 2 inputs, and those 2 inputs should be the key and the message. And then what it should return is some ciphertext C, so we should minimally return an empty string here. And let's see if Python is a little more happy with that. And in fact, it is. So this is the formulation of the encryption value of the encryption function of the Shannon cipher. I should take a little digression here that quite recently I have become convinced that one of the ways to express mathematical concepts is through the use of the Python programming language. This was not entirely novel. In my undergraduate, I took a variety of classes in formal and theoretical mathematics, and my TA in those classes, I happened to have the same TA multiple times, was like me, a computer science and mathematics double major, which was a common double major at the time. This was in the pre-data science days, at least as a major. And my TA expressed to me some frustration understanding what my TA perceived to be computational thinking expressed in mathematical language. And so perhaps this is a nice way my TA told me I was doing poorly in the class, but I didn't interpret it that way at the time. And my TA suggested to me, why do you not simply write your homework assignments in Python? Python as the language of mathematics. And I found that quite persuasive. I think at that time I didn't use the language Python. I used another dialect, perhaps Haskell. It was some form of functional programming language that had these lambdas in it. But it was a positive experience for me because it caused me to think about formal mathematics in roughly the same way that I think about writing code. And that is a compelling and powerful way to think about mathematics. So we will continue to do that here for now. And let's get back in the swing of things. Let me collect my thoughts. So I think the first thing I should do as I'm looking at this is incongruous. So what we will instead say is that we have a lambda which is equal to cipher of ed, and we simply return the tuple ed. And this will get us over to the fairly functional style. One of the reasons I cannot simply write the tuple ed here is I have not defined ed yet, so we are using one of the benefits of functional programming, of sort of delayed evaluation. Let's go on to the next thing. We are sort of now just defining types. So what is the next thing we need to do? We have an encryption technology, and we need the D, which is the decryption technology. So how is this going to change? Well, the second function, denoted D. Ooh, this should be bold. I'm trying to define my terms here, and I can't do that if I don't specify what they are, is the decryption function. It accepts also two inputs. It accepts a key, and it accepts a ciphertext C. So no longer a message. The message is present in terms of the information content of the ciphertext, but it is not readable. And what it produces as output is the original message that is equal to the original message. So how could we perhaps specify this? Well, let's take a look here. Decryption accepts a key and a ciphertext. The ciphertext is, generally speaking, defined here. So we'll note that that is C is previously defined. And then we can decrypt with the key the ciphertext, and that will return the message. M is utilized, so we will specify M, I don't know, I can't do prime, right? This will be, let's see, M out. And then in general, what we would want to do is we would want to assert M is equal to M out. And that will be false for us because we have not actually implemented this correctly, right? So rather we will say we want to be able to encrypt and decrypt messages such that we have assert that EKM, which is the ciphertext, decrypt with the key, the encrypted text, is equal to M. And that does not yet work, but it could work in some other world. And in fact, I think it does work if my message becomes the blank string. Ooh, does it? Does it still not work? Oh, because I didn't change M. Here we go. I want to redefine M here. And so this now works, but it only works with the blank string, and it only works with the blank or empty string, because that's what I'm returning from my cipher. So how can I kind of put this all together? Well, there's one other thing I actually want to do first. Which is, I don't necessarily view these as functions over two variables. And there's one other way to look at this. And I just want to specify what that is quickly. We need not view encryption as a function over two inputs. Equivalently, we can argue that a key is a function, or, oh, that's not what I meant to do. Encryption, let's see, the encryption function is the output of a function that takes a key, and that, let's see, that accepts as input a key, produces as output a text. Now, a message ciphertext, and then produces as output a ciphertext/message. As I'm typing here in Quarto, you'll probably notice that it would be much nicer to do this with Vim keybinds. I did not set up my Vim keybinds. In the specific VS Code instance, I'm using Quarto for inside of my Linux, and I thought, I was like, that would be a lot of work, and I regret it, and I have not been typing for very long, and I also didn't turn off Copilot, which I don't think Copilot is used to teaching abstract mathematics using Quarto Markdown with a IPython kernel, but I've been wrong before. So how do we formulate this? Well, alternate functional implementation. So, this is one way to look at things. And equivalently, we can say we accept some key, and what do we return? We return a lambda of a message, and the lambda of that message returns, for now, the empty string. How does this formulation look different? Now, we say that this is how we make E. We say E is make E of key, and then we apply E directly to them. We can symmetrically do the same thing with decrypt. Do the same with decrypt. So we can actually recycle make E. So we simply say D equals make E. So really what this is doing is this is making a function. Make F of, what were we making it of? It's also of the key. Guess we need a different key. And then we have M out, which equals D of K. That's the wrong type. This should not work. There we go. And then lastly, we should be able to check. We can reformulate the assert statement as well. And so this is now, we specify M, E and D. Is K defined somewhere? probably. Yeah, it's up there. Okay. Um, and then this changes to be d of e of m equals m, which is perhaps a little bit easier to understand. We can also write it out fully, and the way we do that is that d is equal to make f of k, and then e is similarly equal to make f of k. Oh, I didn't change this. Let's fix that. D is equal to make f of k. Please. My the operating system is having no problem keeping up with my copy paste habit, but I had absolutely no idea what I was copy pasting there. String object is not callable. That is pretty unsurprising. I've finally broken this thing. Let's see. So we apply. There we go. And there you have it. Great. So this is the sort of structure that we want our functions to take on, and I've still done absolutely nothing to discuss what an actual cipher is. And so the sort of canonical example of cipher is, well, on this assignment at least, we're using the Enigma machine, right? So let's go ahead and find an Enigma cipher real quick, and I'm going to do that by navigating to the course webpage and looking it up. So here is something I have specified on the course webpage. Motivating example, Enigma. Woo! Typing. It's not as easy as it looks. Okay. What did I do? I pressed a key. Yeah, sure. Please run. Okay, we've got our enigmas. There's a variety of rotors called slow, fast, medium, and reflect, and there's apt descriptions of that in the problem set, I hope. And if there's not, we will debug it and do better next year. What each of these rotors is corresponding to is it's corresponding to a key. Physically, the Enigma device was something that existed that looked much like a typewriter, and its core differentiator from a typewriter is in a typewriter, when I press one key, that key is the output. So if I press an A, I see an A. In the Enigma machine, when you press an A, the key goes into a cipher, and then a different output is created. These rotors are the mapping of letters that I type to letters that come out. And you may note that this is the exact same formulation as the encryption device. So what are we going to do? We are going to change make F to accept one of these rotors. And the first thing I'm going to do when I do that is I'm going to specify that I want one of these rotors. And which one do I want? Well, I want R to equal R's 0. The Enigma machine was typewriter-like, except that pressed keys did not correspond to printing the pressed letter. Rather, they corresponded to some, we'll do single, encrypted letter. We begin with a minimal example. To start off, we arbitrarily select one such rotor for use as a key to a cipher. I forgot to introduce Claude Shannon, which I was going to do. These things are all named after Claude Shannon. It was like a friend of the department. So I've got some rotor, and I have this sort of tool chain built up here where I can take keys, such as a rotor, and produce a function that takes messages and produces ciphertexts. In Enigma, it is initially most helpful to think of messages as a single letter. So we need a function. We need a function that creates a function. The created function accepts one letter and produces one letter. So let's write this up. I think in the assignment, I called this something like rapply for like apply the rotor to a letter. Many different ways to think about such things. Do whatever you wish, right? But here I'm going to use the sort of higher level functional specification. I feel like I should. The Enigma machine was cracked by Turing, whose tutor was Alonzo Church, who invented the lambda calculus. The lambda expression in Python is named after the lambda calculus, and so on. So I highly suspect that the people that cracked the Enigma internally were thinking about these things as higher order functions. And so I'm going to think about them that way as well. And that has been a helpful way of thinking about it to me. And it could become helpful to you as you practice the thinking technique or not. You should make up your own mind. So I'm going to write a higher order function. What this is going to be is this is going to be a lambda expression that contains a lambda expression. So let us rewrite make f. Make f is going to be a lambda function that accepts a key, as above. I do not think this is novel, right? That function is going to accept what I'm now going to say is a letter. Now, there's two ways I would write this out, and both of them are confusing, so I'm going to talk through it. I could put an L here. Feedback I have commonly gotten from students is that, wow, those L's look quite a bit like ones. And I think that's pretty reasonable. That does look a lot like a 1 to me. And then the thought is like, oh, well, then I can use a C for character. We have already used C, that's a namespace collision. We used C for ciphertext. Okay, so what does that leave us with? Well, all of these values and the way the Enigma assignment is formulated are supposed to be capital letters in the, I believe, Latin alphabet, so A through Z. It is not uncommon to use A as a stand-in for alphabetical values, so I'm going to use A here. Lambda of A is going to look through a key, and given the key, is going to figure out which letter maps from one letter to another. How does this really work? Well, let's look at the visual here. We're going to put nothing here for now. What do we write inside? Reference the visual. This is not live code, but I'm going to specify it in a code block for clarity. And usually when I specify this, I'm going to say this is for an email. Okay, so what's going on here? We find the position of some letter in the alphabet. We get the index of the letter in the alphabet, and then we find the corresponding location in the ciphertext. Got it. I'm going to save the alphabet. I'm going to call it the ABCs. I'm going to put it inside quotes. I have a preference for using double quotes for strings because I am a C programmer, and that is how we do strings in C. We are likely to use the alphabet in our expression. The reference solution does not use the alphabet at a higher level course, right? The undergraduates, when we give this to them, we give them the alphabet. We provide it as one of the constants. We say, here, you can use the alphabet if you want. I'm going to use it with the alphabet now because I think it more closely matches the theoretical ideas going on here. I believe many of these ciphers were cracked before ASCII and UTF-8 exists. And so, while it is fun and cool to use ASCII and UTF-8, especially in a C programming class, I do not think it makes sense to use them in the context of a cipher, which is supposed to be existing at a higher abstraction level than the current internal representation of computing devices. So I'm not going to use ASCII. I'm instead going to enumerate the alphabet and use that. So how could we find the location of a letter in the alphabet? Well, if I'm not mistaken, we can use the alphabet and built-in Python functions or methods, and I believe there's one called index, to convert a letter into an index. And the way I think I do that, I'm going to print this. I don't have to print it, right? The code comes out. I actually don't know how this works. None of these things would have run, right? We'll find out. So what I want to do is I want to say abcs dot index. What's everyone's favorite letter? I don't know. Probably we'll do X. I wonder if it's index. Oh no, that's a comma. That's why that doesn't work. Okay, that's completely reasonable. 23. That seems useful. Because over here we have 23. Let's do E. So we did already. And then given an index, we can find the letter at that index within the rotor, which is a key, as follows. You'd think by now I would have come up with some keyboard shortcut to change. I bet there's just a key on my keyboard I can hit and get a Python code block. I don't know what it'd be. So we can take that index, which is 4. And what this is going to do is this is going to give me J back, right? So what do I have going on here? Well, let's make F. With this insight, we can finally implement make F, which realistically should be a no. So let's grab our old make F that we could have done a little better on. We're going to take the ABCs and get the index of A, and then we are going to look at that location in R. This is a function that takes a key and returns a function that accepts a letter and returns a new letter. Let's test it. So first, I have to collect my thoughts. It's a lot of thinking, especially for I'm recording this early in the morning. But okay. First, let's make our encryptor. I shouldn't call it an encryptor. We've been calling it an encryption function. Encryption function. Okay, so finally a non-trivial encryption function. We will accept E, which is going to be make f of R. Simple as that. Wait, what kind of thing is E? I'm glad you asked. I like to check these in a variety of methods. I do this in Python, I do it in C as well. You will learn over time to do it in C. I'm going to demonstrate in Python. I'm going to print E, and I'm going to print the type of E. And what is it? It's a lambda function. And it is a class function. That is a little bit confusing. So we will specify E is a function. It is of type function. I don't know why I wouldn't just put a new line here. I guess I could do 2 prints. E is a function. It is a class function. What happens when we apply E to some letter, such as we were applying E to E. Oh no, what have I done? Okay, not to worry. We're doing just fine. And the manner in which we are doing just fine is as follows. We get a J. This is extremely cool. I don't know if this seems cool to everyone else. It seems extremely cool to me, and so it is okay if this seems not cool to you. But please do accept that it seems cool to me. Okay, so we also have to write D. No problem. It is very easy to write D, but we have to put on our thinking caps. So if we want to unencrypt something, well, we have the cipher. And work with me here, right? To go from E, a message, to J, a ciphertext, we found the location of E in the alphabet, found the corresponding location in the cipher, and then output that value. To go the other way, I think I just have to turn this thing upside down. Let's take a look at that. How do we make D? Well, just do this, right? Is it not just that simple? Right, and so what this means is that I think we are no longer using just make F. I think this is now make E. Let's make sure everything works. And it appears to do so. We simply reverse the process. The manner in which we reverse the process is as follows. We now make D. That should say K. This should say K. Should not say R. Because I should be able to use different rotors. Okay. We take K dot index, and we get the index of K in the ABCs. And this should work. We are now going to make a decryptor. I was saying decryptor. I should be saying decryption function. Don't let me get away with that stuff. I'm trying to be precise and accurate over here, right? We're not trying to cut corners. Not trying to slack off. We're trying to have a good time. So we're going to make the decryption function. We are going to similarly check the decryption function. We also test D, and we will see that it is the same thing. D, 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 D. And then, lastly, we are going to apply D to some letter. Why don't we apply it to J? I think we should apply it to J. That sounds fun. You know, just arbitrarily selected letter, not at all motivated by the ongoing example. And if we do all of that, by golly, we get an E back. That's pretty interesting, because what assert statement was I trying to get back to? Well, let's come back up here. Let's come all the way back up. We're trying to pass this assert statement. Remember this one? We can check our previous assert statement. Wait, did I copy paste all of it? Yeah, that's fine. Okay. Python. Oh, what did I do wrong? Oh, M's not defined. Probably. Assertion error. I have no idea what M is. Okay. That's pretty cool. Let's go one step further. We can test more concretely by looking at the entire alphabet. Why not? So, take Python. We have the ABCs already. And so what I'm going to do is I'm going to write a list comprehension. I'm going to assert that D of E of M I have no idea if the parens are right there. I don't think they are. Okay. Equals M for M in ABCs. Invalid syntax. That is extremely unsurprising. I don't know why I'm even putting an assert there. Let's do this. Many truths. And then what we want to do is we want to assert all of these are true. Incomplete input. That's pretty reasonable. I need two parens, two close parens. Now, I would argue that this isn't quite enough. Why is that? Well, I provided you with 4 rotors. I didn't provide you, I guess. Someone else did that. Let's look at all the rotors. We can test more completely by looking at all rotors. How do we do that? Not to worry, I have a plan. I'm going to write another list comprehension. Okay, so this is one rotor. And that's cool, right? But what is E here? Well, E is make E of R. And D is make D of R. And that code actually works, right? What happens if we just loop over all the R's. Well, we get 4 trues because there's 4 such rotors. And then we should take all over that. Then we should assert that. And if you put all that together, should be pretty proud of yourselves. And so this is a Shannon cipher, according to the crypto book. I don't think I ever heard these called Shannon ciphers. I think I always heard them called like a block cipher or something, which is all good. I'm going to go ahead and grab this Bardo document. What I'm going to do is I'm going to put a YouTube link right here in the top. And then I'm going to upload that onto the course webpage. So as you view this, you'll probably be watching a YouTube video that is embedded right here and has all of the follow-up here. The markdown is, I'm not going to hide it, right? I'm going to put it somewhere. And the somewhere I'm going to put it is going to be under version control on the GitHub I use for all of the course materials. So you'll be able to find it. But you'll either have to look for it or you'll have to ask nicely. I hope you